Yeah. Okay. So there's a little bit of history explained here, just a little bit. Just if you are not familiar with this, sometimes the linear optimization problem, which we shall shortly introduce, is known as linear programming problem. Comes from a time and place when programming meant something completely different. This was pre-World War II. Planning and optimization, when things were still pretty much calculated by hand. Of course, there were mechanical apparatuses, how's that said? You know, mechanical ways of helping computation, but they were not anywhere near the speed of modern software, of course. There have been then subsequent developments that challenge the idea that using the old first versions of the algorithm, which we will introduce. I think the idea of using the algorithm is now no longer relevant, but I do think it's a fascinating algorithm, and understanding how the simplex algorithm works is good training for thinking about how the problem behaves and what makes the problems, the linear programming problems, the LP problems solution, what makes it optimal, and we can learn a lot from it. Okay. I'm not going to go into the details here regarding this various stuff. So the most general format of the linear problem is simple. Well, it's not simple enough, but let's say we can make it far more simpler than this. But let's say that we are minimizing some cost function, and in this case, it's a cost function over a vector is linear, meaning that each variable, we have some set of variables that we express as vectors. Let's say n variables, so they're real valued. So we are dealing with the space Rn, and we are minimizing a cost function that consists of basically it's just a weighted sum of each of these variables. So we can take these costs of each. Let's say that one example of this kind of problem would be that we are dealing with a situation where we're dealing with a process that uses raw materials. And the cost of raw material, each raw material, X1, X2, and so forth, the cost of each raw material is known, and we want to minimize the use of these raw materials. And there are constraints, for instance, that says that in order to produce our quota, we have to satisfy certain constraints. And we want to satisfy those constraints with the minimum combination of costs for our raw materials. And we assume that all of these constraints are linear, so that there are matrices A1, A2, and A3, and we can express this in such a way that A1 times the X, and now this is the matrix multiplication equals B1, where this B1 now has, I mean, this makes no sense if A1 has more rows than columns. So usually this is a flat matrix, has a few rows here, and the number of columns is larger, so it has fewer rows than there are variables. And B1 is a vector that has the size of the number of constraints that there are here. So these are linear constraints, like X1, something times X1 plus something else times X2 plus so forth. And that equals B11 and so forth. So that's the equality constraints. And there may be inequality constraints also. For instance, saying that, well, okay, A2 times, we can express this in matrix format. this could be something like, you know, the maximum amount of each raw material is given, or the combination of certain raw materials cannot exceed something, or something like this. A3X may be something like, you know, at least this much must be used, or this and this together must combine to make this number, and so forth. But they're all linear, so all these are expressible as linear constraints, so that actually each of them is oh, I see the question here that the evaluated the people. So they are not invisible now. Okay, let me. I'm terribly sorry about that. All right. So basically, all these constraints can be thought of that there are single constraints which can be expressed as, and I'm going to write here now, but you know it's going to be visible shortly. So something like C1 times X1 plus, no, sorry. This won't be visible until I finish writing, so don't worry. For some reason, this doesn't work. So can you see that at the bottom of the screen? So all the constraints are of this kind of format. That equality sign may be inequality to one direction or the other. Usually we assume that they are smaller than or equal to, or greater than or equal to. This problem becomes pretty much nonsensical if we allow for strictly smaller than or strictly larger than, if we don't allow equality. We'll see that shortly why that is so. So whenever we can express all these constraints in this with this some you know weighted linear sums, then we can say that we're dealing with a linear programming problem or linear optimization problem. There are now these 4 constraints, and we're actually assuming here as well that all the variables are not non-negative real numbers. So if negative real numbers are allowed, we'll shortly show that this is not a constraint. Sometimes we allow for negative real numbers, but this allowing for only positive numbers is not necessarily a problem. We'll see that shortly. The weirdest thing about this is that even though these are pretty expressive constraints, it follows that this actually, the set of constraints guarantees that the feasible set is convex. So the feasible set is convex, and that's actually good news. That's good news because then this gives us a lot of room to maneuver. Right, let's carry on. So we can always transform this into a standard format where there are only equality constraints. And this is a good thing. Now we can assume from now on that the problem we are dealing with is a minimization of a linear cost function subject to an equality constraint over positive real numbers. So X components are positive real numbers. The only constraint is of the form AX equal B for some matrix A, and the minimized function is linear. Well, how do we do this? There's a procedure that is explained here. Not going to go in depth. We're going to do next week's exercises. We're going to be doing transformations according to this list. So I'm just going to quickly go through this, and the examples will be given next week, and you are expected to follow this list. But very quickly, obviously maximization can be changed into minimization using the theory we already discussed, so that fx, you know, min fx becomes minus, sorry, max fx becomes minus the min of minus fx, because we just minimize the minus fx and then just change the sign, so we get maximization using minimization. And that, if you change the minus into plus, it doesn't change the fact that x is greater than or equal to 0, because it just inverts the cost functions, the cost functions C components there. Inequality can be changed into an equality. If we have an inequality constraint, which is something like x is smaller than or equal to b, we introduce a slack variable. And this can be done also for linear constraints. If we have a linear constraints, we just, whenever there's an inequality constraint, one line of inequality constraints, we can add a new variable to that, known as a slack variable, and assume that that's a positive variable. And then, you know, if it's smaller than or equal to b, it just means that the last new variable then may be 0 if it's equal to b, and it's positive if it's smaller than or equal to b. If it's of the form something greater than or equal to b, we can change it into an equality constraint, introducing a new variable for each of these constraints called a surplus variable. So it becomes x minus y equals b, and the surplus variable is now positive. If x is greater than or equal to b, then this y is obviously negative, bringing positive, bringing x minus y into being equal to b. And if x is actually equal to b, then this y is 0. So it's never need for it to be negative. It also enters the cost function. These surplus and slack variables also are introduced into the cost function, but they have a 0 coefficient, so they don't affect the cost itself. They're just there as placeholders for making these constraints equalities. If there is a variable that really, honestly, could be negative, we can write it in a form where we introduce a new variable, two new variables, uk and vk, both of which are greater than or equal to 0, and we write a new constraint, not a constraint, we replace all occurrences of xk with uk minus vk. Both of these enter the cost function in as one of them as positive and one of them as negative with the same coefficient as xk. So every occurrence of xk is just replaced by uk minus vk, and we assume that both uk and vk are positive. Not going to go here to the alternative way. Whenever there's a constraint that stipulates a variable needs to be non-positive, we can just change this constraint into a new variable that is non-negative, and we replace all occurrences of xk with minus yk. Whenever there's another kind of constraint saying xk greater than or equal to some L, we introduce a new constraint variable yk, which is xk minus L. Conversely, we can express this xk as yk plus L. Constants do not need to be entered into this cost function because the minimization problem is not affected by constants. If you really think about it, if you introduce constants to the cost function, then you can just take the constant off from the cost function, minimize it, and then add it afterwards, because constants are by definition constants, that they don't change. Here's an example, very quick look at this example. Our task is to maximize Z. Obviously, everything here is linear. We just like a quick glance of this problem, example 3.1. So this is linear because it's just, you know, constant times x1 plus constant times x2 plus constant times x3. This is now a maximization problem. So we have to do something to it. It has inequality constraints. Both are this smaller than or equal to, and all these variables are positive. So that's going on there. So only this needs to change. Firstly, we change the, we add, well, firstly, it's a matter of taste, which we do first. We can say that this inequality here becomes a equality by introducing a slack variable x4. So we add, so this may be smaller than or equal to 8, this 3x1 plus x2 plus 5x3. It may be smaller than or equal to 8, okay? By adding a slack variable x4, we can make it equal to 8. So if it's smaller than or equal to, if it's smaller than, then this x4 will be positive. And if it's equal to, then the x4 will be 0. Similarly, the second constraint, we add a slack variable, but it's a different slack variable. Now it needs to be a different slack variable because obviously the slack variables can be different. Also, these enter the cost function here with coefficient 0. And because the original cost functions was a maximization problem, so we transformed this into a minimization problem where we simply changed the signs of all the coefficients in the maximization problem. And x1, x2, x3, now also x4 and x5 are all non-negative. Usually we give this in matrix form. If it's in matrix form, we can give this easily. So the standard format comes in matrix form so that we have this, the coefficients of each of the constraints are given in the matrix A. So in this case, we have 3, 1, 5, 1, 0, 5, 1, 3, 0, 1. And then B, the right-hand side of the constraint is 8 and 5, and C transpose, you know, is given as the coefficients minus 25, minus 7, minus 24, 0, 0. So this is fairly simple. So from now on, I mean, we're going to do some exercises where we transform these into the standard format but for the remainder of this chapter, we shall simply assume that everything has been given in the format where there is a minimized, I'm going to just go up here in this so-called standard format, 3.3. So from now on, I'm assuming that everything here is in the standard format, 3.3, ABC. And we're going to go take a look at how to solve this. We assume now, for argument's sake, that the rank of the matrix is equal to the number of rows in it. And that the number of rows is, well, obviously the number of rows is smaller than or equal to n, which is the number of variables. We do not lose any generality under this assumption because if it has a deficient rank, then the rows are linearly dependent. So either the solution is empty or we can remove the dependent equations and reduce the system. So it doesn't really matter. If you're not familiar with this sort of linear algebra by which we do this, then I really do suggest that you go, we don't have the scope here to go through this. I'm not going to ask this in the exam, so it's not completely necessary and no cause for panic if you don't know what all of this talk about rank and so forth mean, but it is an obvious hindrance to understanding what comes next. So proceed with your own risk if you don't know. Here's an example. If the matrix has, now this is an example of a matrix that has deficient rank. So it has 2 rows, but it's actually singular, meaning that, you know, the rows or columns are linearly dependent. And in this case, the rows are linearly dependent. The second one is 2 times the first one. if we have B1, this is a situation where the first equation is, x1 plus x2 equals 5, and the second equation is 2 times x1 plus 2 times x2 equals 10. Well, obviously, the whole second equation is 2 times the first equation, so we can just leave that, and it has rank 1, and the equation becomes just one linear constraint, x1 plus x2 equals 5. On the other hand, if this constraints right-hand side, it consists of 5 and 11, then this does not happen. We know that we get that x1 plus x2 equals 5, but the second constraint says that x1 plus x2 equals 5.5, and this is going to contradict the first equation. The sum of x1 and x2 cannot simultaneously be 5 and 5.5. So this has an empty feasible set. So it may happen that the problem, here we see, it may happen that the problem may not have a solution at all. Here is an example. So if we just give it in this format, if it's a deficient matrix, if the rank is lower than the number of rows, we may have a situation where it doesn't have a solution. So let's assume first that we check whether the rank is full. If it's not, then we reduce it, and then at that process we will find if there is a contradiction in these constraints. There may or may not be. But let's assume now that the rank is full, in the sense that the number of rows, which we take to be smaller than the number of columns, is the rank of the matrix. So let's examine these solutions to this equation, AX equal B. So you are familiar, if you're familiar with matrix algebra, so if this A were a square matrix that is non-singular. So let's stop here. Let's stop here for a little while, and let's have a short discussion. I'm going to take this off the record. So to make this visually more palatable, we divide the A matrix so that we assume here that they're the first rows from the left, columns from the left, but they could be any rows actually, and we can just rearrange the columns in such a way that we just visually think of them as being the first rows, columns. And this B part here is a square matrix, and all the rest is in this N part. And correspondingly, we take the first components of X as this XB, and then the rest as XN. And if we think about this as two vectors and two matrices, then this equation AX equal B becomes BXB plus NXN equals B. And now this B matrix is non-singular, so this B matrix can be taken as so because this B matrix is non-singular, we can take the inverse of that. So we can solve this for XB, if we know what XN is. And shortly, we'll have something really nice, is that because this XN part, if we just take it to be all zeros, then this N, regardless of what this N matrix part is, this N times XN will be 0. So we can assume that this part is 0, and we get this XB as B inverse times B. So we can solve this equation by just taking some of the variables into account and then assuming the rest of them are zeros, right? So this is what's going to happen. The algorithm is going to be based on this. And we will proceed to go through this proof, not in great detail, but enough detail to convince you that we can always pick some columns. I mean, we just by rearranging the columns of A or the variables of X, if we pick suitable subset of those columns, so that there are as many of them as there are rows in our constraints, then simply by solving this equation, we can solve the problem. All right. So the problem, of course, there are two problems into this that we have to deal with. Firstly, nothing here guarantees that if we just put a bunch of these variables or columns in front of this matrix, rearrange them, and then take there a square part and then take that inverse of that partial matrix, multiply with b, that this resulting xb will contain only positive values. Because remember, one of the constraints was that the values need to be positive. And if we just pick any of them, this B matrix can be such that if we multiply with its inverse, then we get negative values, right? So we say that any such vector x that can be formulated by B inverse B, where B consists of some m columns of A, and those particular values are gained by taking the inverse of B times B, then we say that this is a basic solution. A basic solution, the rest of the variables are assumed to be zero. Basic solutions, well, they may not be feasible in the sense that some of these variables may be negative. If in addition to this, it just so happens that these variables are, the solution are non-negative, so that it also satisfies the constraint that all components must be greater than or equal to zero, then we say that this is a basic feasible solution. And the matrix B, or conversely, the set of columns or the set of variables even that were chosen to be in this X, right? Remember that this is gained from this by choosing certain of the variables or certain of the columns. Each column corresponds to a variable. So some m columns out of the n are chosen. So we call this set as the basis of this, or the matrix is called the basis of this solution. And the variable indices that are there are called the basic variables. And the others may be called non-basic variables or null variables. Null variables meaning that they're zero, null, nada, zip, babkas, nothing. They're not considered. They have no effect on anything. So this is the beauty of it, is that we can do this. And let's see what we can build from that. So if we can find such a basic feasible solution, then maybe we have some solution. It may not be minimal yet, but we have something to go with. So there is one additional problem which it's not a problem in terminology here, but in some situations, some of the basic variables also become zeros. And in this situation, we say that this basic solution is degenerate. It's not a problem per se, but it creates complications for the following algorithm. So we will just go on assuming that the problem is such that there is no degeneracy. So it's never degenerate, so that if they're not zero, if they're not positive, then they're negative, which means that it's not feasible. If they're zero, then we have degeneracy, because there will be more zero variables than there are these basic variables. We can forget about the degeneracy now. It's actually not very common. But if it happens, then we don't need to worry about it, because I'm just producing this algorithm or introducing this algorithm as a way of understanding how the solutions work. And for that, degeneracy is a separate issue that we don't need to deal with here. Timo, who made this material, says that one should never solve linear equations by multiplying with the inverse. The reason is that, of course, the inverse, multiplying the inverse is computationally more complicated than actually just directly solving with something like the Gaussian elimination or some other algorithm thereof. So the inverse, you know, you can calculate it by hand in some situation. And here's a, you know, I hope you remember this. If you don't remember, that doesn't matter. We can use software in most cases here. I'm not asking you in any of the assignments here, I'm not going to be asking you to do things or computations by hand, only going to ask you to write them out on paper as though you had done them by hand. So you can do the hard computation part with MATLAB or anything, just write the answer, you know, just, you know, not intermediates, but, you know, something like the inverse of this matrix is that, and so forth. So pretend if you must. Okay, so let's have an example here. We find all the basic solutions where the matrix is given like this. So it's a very good idea to look at this. We don't deal with the cost function yet. The cost function enters the talk when we have proven some basic concepts here, but because the cost function doesn't constrain the problem per se, it only just says that which of the feasible points is going to be taken as optimal, then we can dispense with that. So in this example, we find the basic solution. So basically there are four columns and 2 rows. So if there are n columns and m rows, can you tell me how many different possible basic solutions there are? How many different ways are there to try to find the basic solution if you have n columns and m rows? Can you already see how many different basic solutions there are? Anyone can answer. I wish I had some stickers that I could have just give you guys so that I would say that whoever gets the first answer gets a sticker. Well, basically you have n columns to choose from, and you have to choose m of them to make a basis. So the number of different, possibly different, they may be, some of them may be same, of course, but the number of different ways of forming the basic solution is n choose m, or, you know, like the Finnish say n yli k, so n yli m. So it's the combinations. If you choose m from n. So this is we can try them all because this is 4. So 4 choose 2. So firstly, we can try columns 1 and 2. So that's 1, 1. We take this matrix 1, 1, 0, 1, and then multiply with the inverse of that. So it's skipped the calculation of the inverse, but you can calculate it by hand or via MATLAB. So you take the inverse of that part. So here it is, 1 minus 1, 0, 1. Multiply the b vector with that, and you get 3, 3. And xn, of course, contains the x3 and x4. So one basic solution is this 3, 3, 0, 0. We see that it's a feasible solution because all the components are non-negative. Choosing columns 1 and 3 doesn't give us a basic solution because 1 and 3 are linearly dependent. They're actually equal, so we don't have to check it at all because the corresponding matrix does not have an inverse. So we can forget about the 1 and 3. Here's 1 and 4, 2 and 3, 2 and 4, 3 and 4. So try them all. And we see that when you choose 2 and 4, it's not feasible, obviously. So this is not going to be feasible because we have negatives here. All the others are feasible solutions, right? So here are the possible basic solutions and the basic feasible solutions. There are 4 basic feasible solutions. So the first solution, 3 and 3, 6, 0, 0, 3, 0.0330, and then 0.063. Those are the basic feasible solutions. Okay? So, in theory, we could try them all, obviously. But if you take n, choose m, and n is a large number, and m is a relatively large number of the magnitude, roughly n over n divided by 2, then this is going to be about 2 to the n divided by 2 or something like this. So it's going to be exponential. It's going to be a very, very big number if we have very many variables and very many constraints. So we don't want that, right? So I'd like to say that you can solve this problem by just trying all the basic solutions and figuring out which one is best, but that's not going to be feasible, computationally speaking. The thing is, if the LP problem, if the linear programming problem has a solution at all, if it can be solved and it has an optimum, then it's among these basic feasible solutions. This is the important and powerful theorem here. So theoretically speaking, we could just try all the possible combinations of these m columns out of n, and see which ones of them are, which one of them is the best. The problem is there are just too many of them. So how do we prove such a thing? This is a good idea, good opportunity to brush up or understand, some proof technique, namely induction. I'm not sure if you're very familiar with inductive techniques. Usually induction techniques are taught in the beginnings of the courses, but here it's done in a fascinating situation. So let's look at the situation. It's an induction on the number of columns of A, and basically we can think of it as the number of columns exceeding the number of rows. Because if the number of rows and columns is equal, then we are dealing with a non-singular matrix and it has one solution. It's a basic feasible solution. So if that solution is feasible, then it's the only possible point that satisfies the constraints. So if it has a solution, then that's it. Right? There's no other possibility because there's only one vector that satisfies, one x vector that satisfies ax equals b. So if that is non-negative, then that's the solution. And if it's not non-negative, it has negative components, then the whole problem hasn't got any solutions because the constraints are contradictory, right? So that's the basis of the solution. So let's say that m is smaller than n and assume that the theorem is true for matrices that have fewer columns than this one, right? We now have a new matrix and we assume that if we took out one row from there, it would be true that they're the feasible solution. If the problem had a feasible solution, then one of those basic solutions were true there. So we're just increasing the number of rows by 1 and assuming that for smaller matrices, this is true. Okay? So let's say that we have a feasible solution. Obviously, I mean, if it doesn't have a feasible solution, then we have nothing to prove because we said that if it has a feasible solution, then it has a basic feasible solution, okay? So let's say that we have some feasible solution, x. So some vector x that satisfies ax equal b, right? Now, firstly, let's assume that some component of x is 0. If some component of x is 0, then we can just partition the matrix in such a way that we remove that 0 component and we have a matrix with one fewer columns, and it still satisfies the problem. This is the algebraic solution here, but it's intuitively simple because we have multiplying with the vector, right? If that vector has a 0 component here, we can remove that 0 component and the corresponding column from matrix, and then we just multiply with that and we'd still get B. And you know, then the same thing then, that now we're dealing with a smaller matrix and a vector and a smaller vector, but we already know from inductive hypothesis that that satisfies the thing. If it has a feasible solution, then it has a basic feasible. So we can find a basic feasible solution for that problem. And there's nothing more to prove in this case. Okay? So let's now assume that all the components of that x, ax equal b, if we have ax equal b and all the components are positive. Well, the thing about this, the thing is, the so-called rank nullity theorem, here you need a little bit of matrix algebra. So basically what you have here is that there is what is called a null space. There are plenty of vectors that make this ax equal 0 true. So there's plenty of vectors that we can choose to make ax equal 0. And if we add, let's say x1, or you know, let's call this y, ay equals 0. So if we add x plus y and multiply that with a, we still get b, right? That's what's going on here. So there is a non-zero vector y such that ax times, that a times x plus y equals 0. Now, this is a bit tricky then. What we can do here is we can take that y and multiply it by some constant theta. So I'm going to just write it here on the margin. So we have this situation that a y equals 0. We have the situation that ax equal b. And we have this situation that ax plus y equal b. Those things are true. These we know because of the rank nullity theorem. We know that y is not 0. I mean, at least one component of this is non-zero. Sorry, positive. I mean, if it's not, then we can just take the negative of y. It's still 0. So we can always assume that y has a some component that's positive. Oh, it should have been ax, sorry.
We cannot see that at all.
The text is not visible? Oh.
No, they are not.
Oh, this is too bad. For some reason, let's take it like this.
No, we are not seeing that now.
No, it's not visible again?
No. Yes.
But it became visible once I did something from here.
Yeah, now we can see it. Again, I don't know.
That's the weirdest thing. Oh, now it's, oh, I had to, okay. Now you can see it, right?
Yes.
Good, okay. So what we're really doing is we're finding this h in such a way that we're taking one of the components and we're calculating this in such a way. You can think of it as, we have this x. It's visually easiest. We have this x vector here. That satisfies this vector here. It satisfies the fact that ax equals b. Now we have this y vector, and if we move along this line here, so we twist it like this vector, then always it's equal to b as well. So what we can do here is 0, right? We can move along this, and move along this axis until such a time as one of the components of x becomes 0. So let's say that here is the 0, here is the y-axis. Sorry, x-axis. So y becomes 0. So this is the trick that we do, is we take from the null space something and we just push the solution vector to a point where one of its components becomes 0. Well then, one of its components becomes 0. We found a solution such that ax equals b and one of the components is 0. Now we can remove the corresponding variable and the corresponding row from the matrix, and we are back to the inductive hypothesis, and we can find a basic feasible solution. So do not worry or despair if you feel like you didn't fully understand what is going on here. But if you didn't, then I urge you later to return to this, because we're going to be using this idea in the proof to come up with the algorithm. We're going to be using a similar idea. Before we do, let me explain the following theorem that we can use, is that if the LP problem has an optimal feasible solution, then it has an optimal basic feasible solution. So not only is it so that if it has some kind of solution that satisfies the constraints, it has one that satisfies the constraints by simply taking the basic solution, but also one of them is optimal. So if it has an optimal feasible solution, it has an optimal basic feasible solution. So we can actually assume that the solution of this problem actually is selecting a suitable number of columns and basically ignoring the rest. One of the things is that if we obtain the optimum at any points x and y, then it is also, the optimum is attained also at every point on the line segment between x and y. So if it has two feasible solutions that are optimal, then all the points that join this feasible, these 2 points are also feasible solutions of, optimal solutions to this problem. And the algorithm is basically based on this. So I'm not going to go through this proof in a way that is very detailed, but let's say that we have an optimal solution to this problem, and x is the problem. So we have this classical, the standard format: minimize linear function subject to linear equality constraint, all components positive. And we have an optimal solution to that. So again, we do this in the same way as before. So if one of the components of this optimal solution is 0, we just go back. I mean, obviously, if this is a square matrix, then there is only one possible solution, and that's the one point that satisfies ax equal b. And if that's a feasible solution, it's the only feasible solution, so it's also the optimal. Okay, so that the basic situation is the same. In the inductive base is the same. The inductive hypothesis is also the same. Let's assume that this holds for matrices with fewer columns. And the first thing we do again is assume one of the components in the solution is 0. Then we can just reduce the number of columns and ditch one variable, and we now have a solution to this, and it's optimal, and we can use the inductive assumption exactly like before. Now, if all the components are positive, so there are no zeros there, then we need to find a feasible solution which has at least one component that is 0. So what we can do is we can find a y that is basically orthogonal to this cost function c, right? So we can find a y in the null space of the matrix A that is orthogonal to the cost vector. And if we can do this, we just move in that direction until one of the, positive or negative of that direction, until one of the components of our x becomes 0. So firstly, if we have this z, which is x minus theta y, if it's feasible, then obviously, because we can have here I'm just thinking what because x is optimal, then if we formulate this z, which is equal to x minus theta y, then C transpose Z must be greater than or equal to C transpose X. X was optimal, so obviously this is a feasible point, so it cannot be better than X because X is the minimum. So this means that if we take a positive theta here, then C transpose Y must be negative, right? We're subtracting something from C transpose X, namely theta times C transpose Y, then that C transpose Y must be negative. On the other hand, we can show that it also, non-positive, it cannot be positive. We also show that it cannot be negative. If we take it from the null space, we can choose. So here's a trick. If one of the components of Y is negative, we can define it in a following way. This is a little bit of algebra where we go into the direction of Y by a factor of theta. So we choose the one that minimizes this coefficient here. And in order to do that, we can prove basically that each of these components are greater than or equal to 0. And let me see, hence, because the weights, the components of this Wi are all positive, we must have this C transpose W must be, of course, by optimality, it must be greater than C transpose X. And then we get this positive coefficient for C transpose Y, which means that because this must be greater than C transpose X, then C transpose Y must also be greater than or equal to 0. So basically what happens here is that we can show that we can find a Y such that it's orthogonal to the cost vector. So C transpose X is equal to C transpose Z. So we can find in the null space, we can always find a vector that takes us to a that makes sure, well, we can make sure that we can reduce one of the variables to 0 as long as there are more non-zero variables than there are these rows. And obviously the minimum is attained at every point that adjoins these 2 points because the cost function is the same. And if we calculate a convex combination, well, it's convexities, and well, this is linear, so it must be equal in a convex combination of those 2 points. And because both of these satisfy the constraint ax equal b and ay is equal to b, then the convex combination also satisfies the convex combination. If we call that z, then az must also be b. So the point here is that we can solve this problem by looking at the basic feasible solutions and by moving from one basic feasible solution to another by use of the null space. We'll shortly see how. So there are n choose m ways of choosing m columns from the n n columns of A. So the number of basic solutions is finite, so we have to check at most this many. But, you know, for instance, if we have 100 variables and 50 rows, then we're dealing with a problem whose size is of the order of 10 to the 29. Here's another theorem that we can look at this. Let's before we go there, I'll have a short. So the extreme point is a point that cannot be formed as a convex combination of any points of the set. And then theorem 3.9 says that the basic feasible solutions are exactly the extreme points of this theta, omega. The visual representation of the feasible set is not very easy, but we can think of it as a, well, it can be projected in a way that it looks like a polygon. It's not, well, if you use inequality constraints, then you can formulate it as a polygon, right? And a convex polygon. But if we use equality constraints, it's not exactly like a convex polygon. It's a little bit more tricky than that to express, you know, because you cannot really say that it's the edges of the polygon, because then that's not really true, because if you are moving along the edges of the polygon, then you know the interior points are convex combinations of that, and they should be feasible as well. So it's a little bit trickier to say that it's, but the visual metaphor, think about it as a metaphor, sorry, think about it as a metaphor of a polygon. And the extreme points, or the basic feasible points, are like the corners of that polygon. It's not entirely accurate, but you know, this will do. So the proof that this is so can be thought of as, if you have basic feasible solutions, they cannot be formulated as convex combinations of other points. If we have a basic feasible solution, and let's take two other points such that it's a combination of two other points like this, convex combination of two other points, another basic solution, a null solution, so this here. And then because the null solutions are null, then we must have this x1 n and x2 n 0. So, oh, sorry, I pressed the wrong button here. So let's assume that they are different. Then it comes down to this x1 being x2 equal x. So we get that this point is the same. It's contradiction that it's a combination of two different points. So it's an extreme point. Assuming that it's an extreme point, I'm not going to go into detail about this proof, but this proof contains the proof that if it's an extreme point, then we can show that in fact it must be a basic solution, so that, you know, if it's not extreme, well, if it's extreme, then it's not a combination of 2 points, and then there's a way of making it a combination of 2 points means that it's not a basic feasible solution. Okay, that we don't need that all that much, but the point here is that if we think about the previous questions here, how do we solve the problem now with this knowledge? How can we transform this knowledge into an algorithm that gives us a solution? That, I think, it's the most fascinating part of here. So we know that the basic feasible solutions are the ones that we want to look at, but there are so many of them that we don't know which to pick. So we would like to pick one immediately that is optimal and be able to prove that it is optimal. So we need a little bit more theory here. So we need to take into account the cost function, because we need to choose the basic feasible solution that makes the problem optimal. And this can be done by the following statement. So this theorem, let's very reasonably look at what it says, and very calmly. This is the last thing we cover today. So let's say that we have a basic feasible solution, meaning that it's X transpose and it's got the XB part and the XN part, and the N part obviously being zeros. And let's say that it's basic feasible solution and it's non-degenerate. Degeneracy makes a problem here, so we assume that there is no degeneracy. Then it's a basic optimal solution if and only if the C hat N transpose, which we define as, we take the cost vector and then we remove from it the null part, really. We take the null part of the cost vector and we remove from it something that is multiplied with the basic part. And now this is a little bit tricky to do. I usually, previous years I've given this online, so I usually do the derivation of this from on the blackboard. So it's a little bit tricky on how to do this. I should try to explain this really carefully. So what does this coefficient that we are calculating here, what does it really stand for? So let me see if I have this. I have only 4 minutes, so I'm not sure if I have this, if this time is enough for me to present this. So let me see if I can make the margin big enough. So firstly, we have that C transpose X. This is not yet visible, but I'll try to make sure that it's visible once I've written it, is equal to CB transpose times XB plus CN transpose times XN. Okay, so we have this situation here. Is that now visible, what I wrote here? C transpose X is equal to this combination right here.
No.
It's not visible? Oh, damn it. I have no idea what is making this. Is it now visible?
Yes.
Okay, good. So basically what we have here is this, we combine this cost into two parts. And it's an optimal solution if this latter part there, the Cn transpose times Xn, if whenever we move Xn, whenever we move this point, so this X point, whenever Xn changes, the net change in this cost function is positive. You see, you can think of this X and that XB, these are vectors. You can think of each variable as a knob that you can turn. Make it more positive or less positive, but it ends at 0. You can make it bigger, or you can make it bigger, but you cannot make it smaller than 0. So in your basic solution, here are the knobs that are associated with the basic solution, and all the n part here, the latter part here, they're all zeros. This is the basic feasible solution. Is this optimal? Well, what happens is that if we start making one of these knobs up, right, then some of these need to go down, or maybe up as well, I don't know. But when we change this null part, then this B part has to change in order to satisfy, and I'm going to annotate again, in order to satisfy that bx b plus n x n equals b. Is that now visible there? The second one I wrote.
Yes.
So this also, I mean, whenever I change xn, I have to change xb because this equation must hold. So how does it change? How does xb change when xn changes? Well, the net effect must be the same. So we can, without the whiteboard, this is hopeless, or a blackboard. This is really truly hopeless without the blackboard or the whiteboard. It's really the zy is explained here. So if we have another feasible solution, y, look at this 3.8. So we can transform the cost of it, C transpose y, is this expressed just like here. And now the basic part here is B inverse B, and then we also multiply this yn with B inverse n times yn. I mean, we're multiplying the whole thing here with, if we multiply this whole thing, the latter part that I wrote, with an inverse of B, we get xb plus B inverse n times xn. So basically this cost function has two parts, the basic part and the null part. And now when we change this a little bit, now xn is 0, but if we change this yn to greater than or equal to 0, then what happens to this cost function, it changes, and the coefficients that express the changes is this, can be calculated in this way. I'm really sorry, I'm really bad at explaining it from a ready-made text. It's easier to explain when I just derive it and write it. I'll try to do that better next time, because this is not, I realize that my wording here doesn't make sense. I'm used to teaching this in writing pen and paper. So I'm going to try to do this in a different way. I'm going to write it in a pen and paper way and explain it one step at a time. And I'm going to do it next time, right? Sorry, this is too hard for me to do this in this way. So I'm going to just do it old-fashioned way. I'll take a pen and paper and I'll write it on the paper and I'll explain what I did, and that way it becomes more easy to understand. Yeah, it's hard for me to explain it from someone else's writing. Okay, we'll leave it at that. As homework, try to see if you can figure this out. I'll explain it better on next Monday. We now have the exercises for the linear optimization are only starting next week, so we still have time. Look at these theorems and also look at the next week's exercises. This week's exercises, model answers, should be there now visible, so you should be able to look at them and do the gradings. There are probably some typos there still, so take note and ask if need be. But yeah, I'm going to stop the recording now.